Hello, everyone. Jonathan and I are going to be talking about optimization motion planning with TrajOpt and Tesseract. So we'll be introducing two new packages, TrajOpt and Tesseract for industrial applications. Okay, so here's the outline. We'll be first introducing TrajOpt, talking about the history, motivation, and capabilities. Then we'll be talking about Tesseract, its motivation, capability, the future, and then will be introduction to hybrid planning using different motion planners. Okay, so I want to give a little background. So at Southwest Research Institute, over the past few years, we've been continually developing different motion planners. Back in 2014, we homegrown two different motion planners, Click and Descartes, followed by leveraging university research to introduce or develop or to integrate Stomp and now TrajOpt for more of your optimization-based motion planners. So give you a little history on TrajOpt. It was actually developed out of the University of Berkeley by John Schulmer. It utilizes sequential convex optimization to solve non-convex optimization problem. If you're interested in the research behind that, the paper's down at the bottom. You can find the literature. To get a little background, so we've been for a while now looking for a motion planner to be able to solve more complex tasks, to be able to be more global optimum in the sense of doing the full process. Instead of just doing individual segments, we wanted to be able to solve Cartesian, free space, all in the same problem to come up with the most optimum motion plan for different industrial applications. And out of that, we took an existing implementation of TrajOpt by John Schulmer, and we integrated it into ROS, which is TrajOpt ROS. And then on top of that, to be able to quickly be able to test the different capabilities of TrajOpt, we developed Tesseract, which is a very condensed, lightweight motion planning environment that has more or less just basic capabilities around collision checking, kinematics, and environment modeling. So some of the motivations behind TrajOpt, I touched on a little bit of these. So we wanted to be able to tackle complex industrial problems. We wanted to also be able to incorporate process planning. So in typical applications like sanding or painting, you have extra degrees of freedom that you can leverage to, say, avoid collisions or minimize Euclidean distance, smooth out accelerations, those type of things that we wanted to be able to have a motion planner that could actually leverage those extra degrees of freedom to come up with a nice trajectory for industrial applications. Another one behind it is we wanted to create more human expected paths. We wanted to reduce the pucker factor. I don't know if anybody's ever done some of the motion plans where you generate it and it actually brushes right past an object. So in industrial applications, our clients don't like that. They don't like it to get anywhere close to the actual part. Say an aircraft, you don't want it to crash into an aircraft. That's very expensive. So we wanted to be able to set, say, distance thresholds. And we didn't want to just do it globally. We wanted to actually be able to set it at different objects, like at the object level. So some objects you may actually want penetration. Say a sanding head, you want that to actually be able to allow to penetrate the surface. So we wanted to be able to have that fidelity of control in our actual process planning. And then we wanted to be able to improve robustness. Jonathan will hit a little bit on this later by plan reuse and seeding. And then we also, as I mentioned earlier, we wanted to have a high-level framework where we can actually write out the entire process and be able to optimize it at the higher level. So I'm going to show a few videos. So here's a complex puzzle piece that we're doing I think it has about 400 Cartesian points with the Z degree of freedom free. We leverage TrajOpt to manipulate that extra degree of freedom to come up with this complex Cartesian path. And it's about 8 degrees of freedom, so 7 degrees in the robot and the tool Z degree free. And then we have another one just to show that this one, so we added more. So say you have a positioner. You have a 2 degree of freedom positioner that allows the spindle to move. You want to solve that all together. So we created not only kinematic chain type capabilities, but just an arbitrary joint tree to be able to solve that. So say you have multiple robots in your environment, and you want to optimize them all together for a complex process. By using TrajOpt, you have the ability to do that along with Tesseract.
I should note, by the way, that the videos that you're seeing here, at least so far, do not have any sort of time parameterization in them. If you see sort of violent swings, just please forgive those for the moment.
So I wanted to talk a little bit about the TrajOpt conversion process. So more or less, it's a direct port of what was existing out there. The main differences between the existing code is we integrated into ROS, we categorized it. We swapped out, originally it was developed using OSG, Open Scene Graphics Viewer, so we swapped it out to use RViz. It originally uses OpenRave kinematics, so we switched it out to use KDL, or we created and I'll talk more about this, but we created a common interface so it could use KDL. It could actually use OpenRave now. Also, it uses Tesseract collision. We'll go into more details on that collision environment here in a little bit. And obviously, what you could imagine with research code, there was a lot of commented out code. So we went through the whole repository, and we're starting to strip out a lot of the commented code that's in there. And we exposed some of the optimization parameters. So there's several parameters that weren't exposed. For us, we needed the ability to change those, so we exposed those to be able to easily use those for tuning your optimization for your application. So this just lists, I'm not going to go into much detail on these, but these, okay. So we have a lot of different capabilities available. So you have Cartesian poses, semi-constrained or fully constrained. You can also define Cartesian velocities, and a lot of these that are available, you can define them as costs or constraints. So some of these you may not care if they're fully met, so you can define those as costs, or if you want to ensure that they are satisfied, you can define them as constraints. You also, for collision, we also have both discrete collision checking, or you can enable continuous collision checking. So now you can actually, it'll use casted collision checking where it'll sweep between two different states, and I'll go into more detail later, but it'll actually, you don't have to finely discretize it too finely, so you can actually now leverage a more discretized trajectory. Joint positions, joint velocities, and one nice thing is about this problem we're talking about, you can actually formulate both, a lot of these costs you define by a time step. So you don't have to define it for the whole trajectory. It can just be for a segment of the trajectory. So say you want to define a, say, Cartesian linear motion in the beginning, then followed by free space, followed by another Cartesian. You can stitch all this together by defining different constraints for different time steps throughout your process, and then optimize it as a whole. Some new cost functions that we've added: joint acceleration, joint jerk, and conical constraints. Some of those are nice for, say, welding or paint applications to be able to leverage a conical type degree of freedom. A new one that's not listed on here, we're in the process of, implementing time parameterization as part of the optimization. So currently today, a lot of that's done post trajectory planning. We wanted to actually integrate it into the optimization to be able to actually leverage time itself to come up with better trajectories. So through all this testing, we started out with transitioning TrajOpt over to ROS. And we wanted, the whole point of the research and development was to understand the full capabilities of what TrajOpt had to offer for industrial applications. So out of this, we decided to create a very lightweight motion planner to be able to quickly change things and be able to test the capabilities of TrajOpt. Some of the other things that were required by TrajOpt, it requires convex collision checking. So you can't do detailed mesh collision. It requires that minimum translation vector between two objects to understand how to get two objects out of collision. So it can handle, say, convex shape to a detailed mesh, so that works fine. So you have to be more diligent about how you define your environment and your collision objects to be able to fully leverage TrajOpt capability. So if you have, say, the robot moving, you probably want to model it all as convex shapes, and the world can be detailed meshes, or vice versa. If you have two detailed meshes, you'll actually get some weird behavior out of TrajOpt. We wanted access to kinematics and dynamics to be able to take into some dynamic cost constraints and parameter limits. And some of the other motivations behind it is a lot of times in industrial applications, you want to be able to switch out in and out different types of objects without having a performance penalty. Multiple robot planning. So we wanted to be able to have large degree of freedom problems and be able to solve it. In some cases, we wanted to be able to dynamically build the scene itself, where you can build the kinematic chain just from code. And kinematic chains and arbitrary trees. And then, as I mentioned earlier, we wanted to integrate time parameterization. And also, we wanted a test bed. So we wanted to be able to quickly be able to try different things to come up with more optimization, or to optimize ways things are done around environment modeling, collision checking, kinematics and dynamics to see if we can come up with faster or higher performance ways of doing these things. So we wanted a very lightweight test bed to be able to test these things very quickly. And continuous collision checking was one of the big things that we wanted to be able to test, because that's very important to us with current existing capabilities. So what you currently have in Tesseract is you have the core packages. It's platform agnostic. We intentionally did it that way. We wanted the interface API to be independent of ROS in the way that maybe it could be used outside of ROS if needed, so you're not tied to that. And then on top of that, we built Tesseract ROS, which is actually the ROS implementation of that core package. Then the main one I'm going to be talking about today is Tesseract Collision in more detail. The other ones are just so your messages. We created an RViz plugin for it and some monitoring. The one interesting thing about the Tesseract monitoring is we've had several cases where we want to actually not use it for the collision checking, not use it for motion planning. We wanted to actually use it for monitoring the robot. So say an operator picks up a teach pin and he starts jogging it, right? Sometimes they mess up and run into collision. So we wanted the ability to add onto this where you could have something monitoring the joint state and doing really fast collision checking to, one, stop the robot if the operator is going to do something and collide with the environment, or to be able to do those type of things. So some interesting things. So we took the existing implementation. So we started with the Move It implementation for the environment. We started off with doing that. We decided to simplify things, and we wanted to condense everything into a single environment instead of two separate ones, just to make it easier to manage for quickly testing different things out. And profiling. We wanted to profile the code to find out where it's taking so long, because as most people know, a lot of the motion planning time is spent in collision checking. So we wanted to be able to quickly profile it, identify. Some interesting facts is we noticed two different things when we did this. One, the use of a fine 3D matrix. You got to be very careful when you use these. Depending on how you construct it, it actually runs SVD under it. So we found when we profiled it, 20% of the code at the time was spent executing SVD. I was like, why is this happening?
For clarity, you mentioned eigen, right?
Yes, eigen. This comes from the eigen library. So we were like, what is going on? Why is this happening? Well, it turns out that the way it gets constructed, because it has other uses for scaling and skewing, that it has to run SVD for inverses and those. It can't leverage the quick ways of doing this. So we went through and stripped out a fine and replaced it with isometry matrices. So by doing that, it alleviates the user, because the user's got to be very careful on how he uses those, or he's going to pay a huge penalty when using those. And the other thing we found is a lot of the times the environment was being, every time you make a collision request, and the current capability, it was reconstructing the entire environment. It was building it from the scratch up for every collision check. So you can imagine a lot of these motion planners, they do 10,000 collision checks. So that's a huge penalty you're taking to reconstruct this every time. So what we did, we switched it, and now we created a collision environment such that you construct it once, but we provided the ability to clone it in a way that it can be used in multiple threads. So in most cases, it's a lot cheaper to clone it, say 32 times if you have 32 threads, versus the number of collision checkings. And so currently, the current state of implementation for the collision library is we have Bullet implemented for both discrete and continuous collision checking. It's actually casted, so it doesn't take into account the joint kinematics sweep between it. You give it two different states, and it actually sweeps the volume between two different Cartesian. So it's a linear interpolation between the two. So you still need to discretize it such that it's more of a linear approximation of your actual motion. So one of the cases, say your arm's here, and then your arm's here, and you say plan a motion, you have an object in front of you. It's not going to see that because it's going to sweep the volume from left to right, and it's not going to check that. So you still need to divide up your path such that you can take advantage of this. And then we currently have FCL implemented for discrete collision checking. It's an experimental state. We've actually been working with the FCL maintainers, which have been great about getting some of this convex collision checking fixed and integrated. So here's just an example of how the continuous collision checking. So the green box is the obstacle. The three red boxes are the trajectory. And you can see it sweeps the middle box to the left box, and it detects a collision. And it actually progresses it, pushes it out away from it to create a collision-free trajectory. Here's just another one where you have, say, a glass upright. You have a Cartesian where you define the orientation as fixed, but you leave it to change position. So it's able to push itself out of the sphere. I think I have one more. And then here's a complex, just a free space motion planning, a high degree of freedom problem where it's given a joint interpolated trajectory, and it's able to use the convex collision checking to push itself out around the table and come up with a collision-free trajectory. Next, Jonathan's going to be talking about how you can leverage both of these packages for hybrid planning.
Thank you. Hello, everyone. My name is Jonathan Meyer. I've worked with Levi at Southwest Research Institute doing a lot of sort of industrial applications with traditionally with MoveIt and OMPL planners. RRT is my friend. If you look over here on this picture, you'll see actually one of our newer robot systems. This one's actually meant to sand airplanes. It's a 22,000-pound vehicle with a 4-meter robot arm on a giant rail that drives up to platforms, scans its environment, and does all of its motion planning dynamically. And so we've had a lot of experience with the do's and don'ts of sort of dynamic motion planning. And this is what makes me so excited about the opportunities that sort of TrajOpt and these optimization planners allow for us. So what can we do with it? We can do lots, right? Traditionally, we use sample-based planners, and I'll talk a little bit more about that in a moment. But what optimization allows us to do is sort of expand our horizons to solve more problems and put more constraints on our paths, especially in the time domain, right? So we usually, like Levi mentioned earlier, we get a path and then we try to sort of massage the path afterwards to make it achievable by real robots. And with optimization, right, we can do it in situ, if you will, right? If you have a rail like on this robot and it's really slow compared to the rest of the system, we can actually use use the optimization to sort of allow the robot to take up slop in a linear trajectory. Like you want to maintain a constant speed, and the rail accelerates really slowly. Well, the arm can shoot out in front, and then the rail can catch up. And it's a really awesome opportunity to solve more problems and make them more reasonable. And I should note real quickly, when I mention, if I say under-constrained path planning or anything like that, as opposed to a lot of the mobile robotics world, we actually usually have way more actuators than we have like degrees of freedom in our problem. So say you wanted to put a sander up on the wall, right? You can often just rotate. It doesn't matter, right, what the orientation is, as long as the z-axis of your transform is pointed in the right direction. So what is optimization good for, right? It's really good for high degree of freedom systems, right? There's this curse of dimensionality, right? If you have a large space to search, it very quickly becomes just totally linear. The complexity of your algorithms explode, right? RRT and Descartes and these other planners that we do have lots of issues with that, right? And like I mentioned earlier, optimization allows us to take into account a lot more dynamic costs, things like accelerations or velocities. But, and that's a big but, right? There are still problems, right? So the optimization planners have a couple of downsides, right? One of them is, to quote David Liu's presentation from yesterday, trillions of parameters. Usually when you set up one of these things, you have to give weights to everything, right? How expensive is this compared to, how expensive is holding your normality compared to being smooth in time? And it's really hard to put a number on that, right? What happens in practice, right, is you just tweak it until it looks approximately right and does the right thing. And you hope that you don't ever come into a situation where it doesn't. The other problem is that optimization, by its very nature, is incredibly sensitive to initial conditions, right? So what I mean by that, right, is that it's some form of fancy gradient descent, right? You sort of fall into the local minimum of your path. So the robot arm has many configurations that it can reach a particular point at, but the cost to move from configuration 1 to configuration 2 is enormous. And so even with the optimization, you may not find the best solution, I guess is what I'm trying to say. So to sort of motivate this, let me show you a video, if I can find my cursor. Thank you. Let's see. And a video of an optimization problem that I want to illustrate. So this is motivated by some work going on in ROS additive manufacturing by Victor Lemon. And it is sort of deposition. He's doing additive manufacturing by sort of weld wire on a drum barrel in front of him, and he has paths. And this is the naive path passed through TrajOpt, right? Probably don't want to execute that, right? And you can kind of imagine, right? There's all these points wrapping around the barrel, and the robot starts sort of up in the air at 90 degrees. And so some of the points are on top, and some of the points are on bottom, and the whole system just sort of, some of the robot poses go to the top, and some of them go to the bottom, and it sort of wraps around the barrel, and it can't quite handle it, right? And it'll fail to plan. You can go ahead and let it finish. Thank you. And so you'll see the same behavior here again. And so what's the solution to this, right? Well, you could seed it, right? I could actually position the barrel at every time step so that this works. But what happens if your path is slightly different, or you have a problem that's hard to specify that seed? Or a lot of times what we do is we don't know what's in our environment ahead of time. How can we intelligently pick seeds or figure out what's going on? And that's where, if we switch back to the slides, that's where we use sampling planners. So imagine something like OMPL, or here I'll just give you the brief on Descartes. Actually, Sean Edwards gave a great presentation a couple years ago about Descartes, which is a sort of Cartesian motion planner. And I refer you to that for details, but just to give an idea, these sort of dots across the top are user trajectory points. So it may be like, I want the robot to be at exactly here. Or it might be like, I want the robot to be approximately here. And what we try to do is expand all of the valid solutions for each of those, build a big graph, and search it, right? It's sort of the regular grid equivalent to what OMPL and RRT sort of does. And it's brute force, but it really works well because computers are fast and we can do everything in parallel. So we get a, sorry, let's see, where'd it go? Well, all right, I'll keep talking, sorry, while we find the video. But it's subject to, it still has its own problems, right? Discretization doesn't work well in high dimensions, and it has its own, Discretization doesn't work well in high dimensions, and you end up with little quirks of motion planning, things where if you only search here, here, and here, your robot path will be moving along, and then you'll see a snap that happens. And there are ways to fix it, but that's where doing something like TrajOpt actually makes a lot of sense. So we actually need to go to the next video here. Let's see. That's the wrong one. So, excuse me. Yes, that one, please. It's open at the bottom. Okay, so here's a plan that comes out of Descartes, right? So you can see that it moves around and it does approximately the right thing. So if I just highlight one thing, notice a couple things here. It's moving along, and at some point it hitches, right? And in fact, if you let it keep going, it'll just stop here and hold it still. And you may say, okay, that's reasonable. What ends up happening in reality, though, is that these accelerations cause all kinds of problems when you're actually trying to be extremely fine, like sub-millimeter in your accuracy in placing things. And so what we do is we take the Descartes plan and run it through TrajOpt. Surprise! And what you get is this extremely boring, extremely smooth path. And if I've learned anything in my time doing industrial robot stuff around things like planes, is that boring is good if it works well. So I think you get the idea, right? Essentially, the barrel just keeps turning, and it never really accelerates except at the very beginning and the very end. Yes. So last but not least, I want to talk about sort of. I think some people will extend this conversation, which I'm really actually excited about. This is one other really cool thing that sampling to TrajOpt lets us do. Imagine you didn't have just one path that you were trying to do, but many paths together. Say a lot of welds on a part, or many rasters when you're painting something with a robot, right? What you can actually do is construct all of these graphs, append them together, and search the whole thing, right? And then you run your optimization locally across each of those components. And what that does is give you very smooth paths that sort of intelligently choose when it has to change configurations. In practice, what it means is that we can be extremely robust in the sorts of things that we do. And so just to illustrate another, perhaps not super exciting example, but this is a 9-degree of freedom system, right? It's 2 degrees of freedom on a rail, 6 degrees of freedom on the robot, and then sort of a free rotation at the bottom. And it solves fairly quickly. We're talking, 3 or 4 seconds, and produces paths that are pretty reasonable. So anyway, you get the idea. It just keeps going. And it's, I should say one more thing, it's deterministic, right? And that's a huge deal for us, is that you will get, for the same inputs, the same path out every time, and it makes it very easy to debug things. So, okay. Okay. So you want to finish this off, Levi?
Okay. So if you're interested in finding the code, we've got the core packages out on GitHub under ROS Industrial Consortium. Also, Jonathan Meyer has a lot of these examples out under his hybrid planning experimental repository. And also, what?
I apologize for the state of the code. I promised it'll be better. I'll clean it up. But I wanted to get the examples out there. There's lots of them, so.
Yes. And also, if you're interested in finding the original implementation, there's a link to his code. It also has documentation related to it if you're interested in that. My contact information and Jonathan Meyer's.
I should mention one last thing in my final 5 seconds. If you have ARM navigation problems or test cases that you're interested in having solved, please come find us after this presentation. I really want more examples to work off of.
Thank you.
Got time for a quick question. Is that one headed to the mic? Yep.
Hi. So is this are those two planners compatible with MoveIt? And if not, would it take a lot of effort to do the integration?
So we've been working very hard to get this into MoveIt. There's going to require some additional changes. We've been working with Dave Coleman, mainly because around the collision checking, it really changes a lot of it. But you get about a 5 to 10x improvement in motion planning by this alternative method. But yes, we are working to get this in to move it.
Cheers.
Fantastic. Thank you very much, Jonathan and Levi.